всем представить профессора Серджио Мендеса из университета Луисвилля, факультет физики и астрономии, начальник лаборатории, довольно крупной лаборатории фотоники и специалист в области фотоники, интегральной оптики и волоконной. Профессор родился и вырос в Бразилии, получил степень бакалавра в университете Сан-Паулу, степень магистра в Рио-Гранде. Потом долго стажировался и написал Ph.D. в Аризоне, в самом большом исследовательском центре интегральной оптики в США. И сейчас работает в Луисвилле и ведет несколько проектов, очень междисциплинарных, но средством получения информации, в которых является свет, изучение, и он расскажет об этих проектах. Я полагаю, что переводить-то практически не надо будет, у всех скиллов достаточное знание языка. Ну, хорошо. По мере накопления информации я буду делать краткие вставки на русском, хотя, судя по публике, это совершенно не нужно.
Ты не засыпай, только комментарии все-таки делай.
Хорошо. Let's start, Professor. Well,
Thank you. Thank you. Can you all see these slides well? All right. It's glad to be here, and I had a little visit to the company across the street, and I feel very good. I did work in industry for many years of my career. I started working back in Brazil in optical thin films and lens design, and I also got my Ph.D. later from University of Arizona, and then I worked for a company doing some integrated optics, very, in a way, closer to what you have, and I could see today. But as at the university, and in particular, I'm using integrated optics for different applications. In particular, we are looking a lot actually on the interface. Of course, my background is in physics, photonics, but I'm looking at a lot of the problems that goes in interface between chemistry and biology, and we are looking at how we can learn a lot of things that happen in particular molecular films using photonics tools. And in order to do that, we have to do a lot of micro and nano fabrication. Are we doing the translation here? You stop me anytime if you need it.
вопросы задаем по ходу.
Okay.
Okay.
So we're going to be discussing and use the integrated optics for some applications. And I'm going to discuss following Roman's suggestion. I'm going to talk to you today about these two topics here. One is use of single mode integrated optical waveguide tools in order to do optical spectroscopy of molecular films. And the next one I'll talk to you is how to implement on how to improve, enhance the fabrication of fluorescent sensors using some concepts of integrated optics. So on the first one, here a key part of this work is, this is for people in biology and biochemistry, is there is a very relevant problem here, is to understand, we all, people in those fields, they can take a protein, that is, here's a protein represented by people in organic chemistry, and here's a protein represented by a physicist. And this protein has a lot of heterostructure. It's a very three-dimensional entity, and it's very heterogeneous. And there are places on this protein that are active, and some of them are inactive. When you take this entity here, this 3D entity, and immobilize on a surface, many effects can happen. For instance, if you're looking at the binding of a particular ligand to this protein there, you may have a configuration that this process is favored. For instance, on the left here, this is what people in biochemistry would call a lock-in key. You have a configuration that, for instance, you can have this ligand fit there properly, and you have the reaction going, for instance. On a configuration that you have like in the middle here, on this process, for instance, you have the active site hidden from this process, and you can no longer have this binding process there. So this is an unfavored situation. Another possibility is that when you have this binding of this protein to a surface, this protein may change its three-dimensional conformation and lose its specificity. A lot of things that are unique from the biological material, it is its three-dimensional structure there. And once it changes its conformation, it no longer have this specific binding of a particular ligand there. So in this case, that's a case that this process would be either inhibited or you lose its specificity there. So the binding process of biological material to an interface there can have several impacts on the biological functionality of a particular molecule there. So many times people in biochemistry, biology, or chemistry, they put an enzyme on the surface and that enzyme loses its specificity, how it acts. And there are many cartoons or many hypotheses that something is happening there. But there are not many tools, analytical tools that can come and tell exactly what's happening on the surface. So what we're gonna do, we're gonna use these integrated op techniques to approach that. That's the motivation here. This process here, this immobilization, can have tremendous effect in, as I said, can affect the affinity of that process, the biospecificity, the reaction rate, and all this has tremendous impact in many technologies, like biosensor. If you define a biosensor, that you're relying, for instance, on this process to happen, but if you have geometries that are looking more like that, you're going to lose your specificity, your activity there, and you're no longer going to have something that you would expect to be happening there. So these are important there. Another area of application, for instance, a lot of medical implants. You are taking an inorganic material and implanting on a living organism, and how this growth of biological material goes on top of that inorganic surface is going to determine if you're going to have, for instance, rejection or not. If that biological material is growing properly, or it's going to have a different behavior there, it's going to determine if that medical implant is going to be accepted or not. Also, many catalytic process there or any interface depends on the immobilization of biomolecules to those solid liquid interface, and we depend on that. And many separation processes in chromatography also depends on the immobilization of biomolecules to interface. So that's the motivation for our work that we're going to attack using the tools of integrated optics. Let me tell you from the beginning, what is the gold standard out there that is doing today this kind of job? There are many tools in optical tools like ellipsometry that has been used in the past to understand when you have very few molecules on the surface, to understand this process. Also, quartz crystal microbalance, it has been used for this process. But nowadays, the technique that is the most sensitive and most impressive in terms of giving information of this process is known as surface plasma resonance. The technique is extremely simple in a way. What you have on this interface here, you have a piece of glass that is coated with 50 nanometers, roughly, either of gold or silver, a noble metal. And you shine light there, and shining light on a gold film usually get a lot of reflection. Well, but if you come from a high refractive index here, and you come with light there, what happens at a particular angle that you have there, when you solve Maxwell's equation there, you find that there is a surface wave, that's the plasma wave that can propagate. And when you solve this Maxwell's equation, you find that that surface wave propagates with a certain speed. When this light wave here, when you have this light wave and you project to the tangential component and you match that tangential component there with the speed that you have for your surface plasma wave, you transfer energy from your light wave to that plasma wave. And if you measure reflectance here, that reflectance goes down to 0. Yes?
Please not so quick and more distinctly, otherwise we're lost. Not so quickly.
Okay, apologize. You want to recap a few words here?
No, but
You
not
good?
so.
Okay, thank you. Do you have any point that I need to clarify?
No, I understand, but I understand that I will, in a few minutes I will lost your ideas.
Thank you. Okay, please stop me again if I keep, in American talks, I mean, we have a short time and we want to say a lot of things, so this is something that is inherited. So stop me again if I start to speed up again. All right, so we have this gold film and we come with light at a particular angle, this reflection goes down to 0. This is what is represented here. This is the angle of incidence there. This is reflectance. This reflectance starts to, this is what you typically what you have. You have prism and you have water. You have prism, you have gold film, and you have water. And so this goes very high here. This is hitting the total internal reflectance of the prism water interface there. And this goes very high. And then you get very high reflectance there until you start to hit that resonance that I was mentioned to you, that you start to transfer energy to this plasma wave there. And then when you do that, your reflectance goes down to 0 and then comes back again. And this angular width here has to do, it is linked to the propagation length of your plasma wave there. So this is limited by your metal film. So you get a very characteristic curve here that is this sharp decrease in the reflectance there. And this only happens to a particular polarization here. This is polarized light. And this is what this is good for, okay? Well, what happening here is that this particular position of this peak here is extremely sensitive to what is happening on the interface. Because when you transfer energy from this light beam to that plasma wave, what you have is actually, if I look on this interface here, what you have an exponential decay of the electromagnetic field. So anything that goes at that interface there, if you disperse a molecule, if you take a protein and put it close to that interface, it's going to locally change the refractive index. When you locally change the refractive index, for instance, that peak is going to move. And that's what the technique is used for. Anything that comes to this interface is going to move that reflectance, this sharp reflectance band there. And by looking at this shift, you can look back on Maxwell's equation and you can tell how much changed the refractive index, and then you do some math and you find out what is the mass that you have of your particles on the surface. So that's the technique that currently the pharmaceutical industry is using for finding binding affinity of the new chemical drugs that they are developing. So for instance, they mobilize those new chemicals on the surface, and they send through. First, they need to find the binding affinity of a huge library of proteins, if it's going to bind or not to those, for instance, that new chemical. So by looking at this, how much it shifts there, you can see how that process is going or not. Okay? So that's the gold standard out there. Looks like you have a question?
Yes, I want to understand, I'm right or not, the energy from the from the light coming to the surface, it change its polarization or it's absorbed by the molecules. You see the resonance. The energy must can't disappear. It can transfer in another forms of energy, or it may change the polarization. This is why we see nothing. What process you are speaking about? I can't understand. Absorption or changing the polarization?
It's going to be lost as the surface, as you excite the surface wave, it starts propagating, the metal absorbs light. So it's going to be attenuated by absorption of the metal. So it's lost. It doesn't come back. When you hit this angle here, it doesn't come back, and it's lost on the propagation. And this propagation goes 100 microns, and from those distance there, you do a Fourier transform, you get the angle with all your resonance there.
Thank you.
Okay, so you take here. This is typically a few degrees, and you look at shifters here, and you can as soon as you start seeing the shift there, you can resolve. That's what you can detect on the surface there. So this is the gold standard. If this actually has been this business was initiated in early 90s by a Swedish company called Biocore, and this business was bought by GE, and has been the gold standard for those people. And if you ask those people, how much you can detect, what is the figure of merit here, what is the limit of detection you can get, they're going to give you something like this number here, 100 picograms per centimeter squared. This is the minimum amount of protein on the surface you can detect. This is very important for even if you're detecting disease or if you're detecting new the binding of you. This is a very important figure of merit. What the vendor of this tool is not going to tell you, what he has in mind in order to detect this time number there. Well, in order to detect this number here, you need to resolve things that are 10 to the -4 of a degree. So you have here 3 degrees, and you're trying to resolve something like that. So this is a time change. All the people using this, they never consider that you can detect that. So this number here is overrated. It's way high. So most likely people would consider more like in the range of nanograms per centimeter squared is the limit of detection technique. What is more amazing here is that you have a helium neon laser, you have a detector here, you have a prism, you have a piece of glass, and you have a gold film, and the vendor is going to ask you for $400,000 for this piece of instrument. And the money they're asking for it is actually in order to mechanically and thermally stabilize this whole thing. Because anything that locally changes the refractive index there is going to create a jittering on this process here, and it's going to kill your limit of detection there. So this is the whole price that you're paying here is for tremendous stabilization of this process here, of this environment there, in order to get something that is close to this limit of detection. Okay? So this is what we have in mind, and we are working in terms of to develop something that goes beyond to this.
Maybe somewhat in Russian.
Sure.
Какие-то пояснения нужны. То есть вот про то, как белки себя ведут на поверхности, этим очень интересуются биологи. Как первые белки садятся на поверхность, как потом вторые к ним цепляются, как это все происходит. У них сейчас нет адекватных инструментов для решения этих задач и ответа на этот вопрос. Вот поверхностный плазмонный резонанс – это золотой стандарт, которым они пользуются, но он страшно дорогой и страшно нечувствительный. Вообще, когда биологи разговаривают про поверхности, про то, как на них садятся белки, они всегда такие возбужденные, это прям очень надо. Я, честно говоря, не знаю подробностей, но, видимо, это действительно актуальная задача. Вот. Вот это золотой стандарт. Дальше начинается то, чем занимается профессор, и оно гораздо интереснее.
А чувствительность этого метода?
Вот 100 пикограмм.
Вопрос, Ром, переведи, пожалуйста. Я смогу сам на рудиментарном своем, но у тебя лучше получится. Здесь у него гелий-неоновый 638, да? Соответственно, что даст перестройка длин волн? Потому что, как бы возбуждаются уже другие молекулы, да, и
Вот об этом, Паш, как раз будет дальше подробно рассказать. Вот ты правильно вопрос задал.
снижают, извините.
Окей, if you do it. Thank you.
What is the concern? My Russian is not that great yet. So.
The question was about wavelength and wide spectrum. What will occur with the wide spectrum? But you will discuss it later.
Maybe not. Maybe I should tell, because this is not, I can't tell. If you come with white light here, is that the concern? Broad spectrum?
We are talking about tunable laser with wide spectrum on different wavelengths, and with a different power, and maybe not a continuous wave, but pulsed lasers.
Okay. So this experiment actually you can do with a broadband, and instead of looking for different angles here, you just send all the colors at one angle, and you look at that reflectance against wavelength, and you're gonna get a similar curve here.
Independent from the wavelength.
You come with several wavelengths there at a broad spectrum, and at one fixed angle. And what you see is that one particular, if you have the wavelength here, what you would see is one particular color, the reflectance would go down.
I see.
But why this is not convenient commercially is that you need to have, this width here depends, for instance, in this case, you want to have one angle over a broad spectrum, you need an extremely high collimation. You need m squared, a Gaussian beam with very little divergence, otherwise it's going to broad on the spectrum here. And it's cheaper to use just a single wavelength from a laser, and that you can have very good Gaussian beam with very little divergence there, than use broad spectrum. That's why it's implemented on the angular version and not on the wavelength version. But you could do the experiment if you like. Okay, so this is the background. This is nothing that we do. This is actually the background of what we are fighting against, and I hope to show that we can do something that goes beyond that. This is more of a cartoon that, so what we want to detect, we want to get, what we are fighting is detecting very small amounts of molecules on the surface. And if you go and try to use your conventional spectrophotometer there, when you have very few molecules on the surface, you send a light beam, most of the light almost goes transmit through, to convert that to absorbance. You get things that are 10 to the -4. That's about the limit of detection of most spectrophotometers there. So people, a long time ago, they noticed that you can improve the sensitivity of detecting that film there if you bounce a few times. So now every time you bounce here, you enhance your analytical signal, and if you bounce like 10 times, you roughly get an enhancement of 10 times. So the more bounces you get, the more signal you get, and you will have a better chance of detecting what is on the surface there. So what going to do is, what we're proposing to do is, we know here that the more bounces, more signal. We want to shrink that configuration to the most, more and more and more. So we're going to take geometries like 5 millimeters, and we're going to bring down to 500 nanometers. So instead of like 10 bounces there, we're going to have 10,000s of bounces per unit centimeter. And this is obviously using a ray picture of a guided movement. So that's the configuration we are looking for. It's confined as the most we can. Obviously, when you go to regimes like this model of ray picture doesn't tell you the whole thing. I think most of you here, I believe, should I assume work in integrated optics? No, okay, so when we have films confinements that as thin like this, we have a very strong interference effect. and it's not enough to take the ray picture there. What we should see is that what we have is actually, for instance, we have a refractive index profile like this. This is our substrate, this is our thin film waveguide refractive index, and we have our cover here. Typically, for instance, this is going to be glass, this is going to be water or air, and this is the thin film that is guiding the light. And so this profile here, as when we solve Maxwell's equation, we see that, and we consider all the boundary conditions that we have, so essentially solving wave equation and boundary conditions, we're going to find modes. The thicker we make this waveguide, and the taller it is this peak here, more and more modes I can have inside my waveguide there. And this is very similar to people familiar with quantum mechanics. This is similar to the potential well there. The only difference now, instead of having a well, I have something that goes on the opposite side there. So I have more and more modes. Those are the effective index of each eigenfunction that I have that represents the intensity of my electromagnetic field. And we see that an oscillatory behavior inside my high refractive index, and there is an exponential decay on the lower refractive index part there. And it is this piece here, well, actually this part here, it is this evanescent field there that we use to probe whatever comes through this interface there. It's that part there that we call the evanescent field that's going to be used for detecting things that are on this interface there. So an important figure of Meriter here is, let's say we have this waveguide there in yellow. If we put something here that absorbs light, and we want to compare, given a particular film there. Let's say this film, if I come with light straight through there, I get some absorption. We call that absorption in direct transmission. And let's say that I measure the absorption through a guided wave. Let's say I have a guided wave with a certain profile there. I have a little exponential field there. And this propagates from here to there over a distance L there. And I want to calculate this figure of merit that we call sensitivity. That's the ratio of the absorbance measured through the waveguide, normalized by the absorbance that I would get through direct transmission. And this number here, if you do the math, it depends on two factors there. First, it's going to depend on the ratio between this L here to this thickness of my absorbing field. The larger this ratio, the longer you propagate inside this guide there, the stronger is going to be your enhancement there. So this is playing, is helping us, but we are going to pay a penalty here. We pay a penalty because this light beam that is guided there, not the whole beam, is seeing the molecular film. There is just a small fraction that is seeing the molecular film there. So this factor here is essentially, this is the total field, the electric field square over this whole space so that you go across section there. This is the normalization, and the factor that matters is what fraction of this electromagnetic field is inside my field of interest there. So this number, typically, this is way smaller than 1. Typical numbers here is 10 to the -3 there. So this is a serious penalty. But when you look at the ratio between the propagation length you go inside the waveguide compared to the thickness, we're talking here films that has 1, 2, 3 nanometers, and you're comparing here with length that are several centimeters. This number is way huge there, 7 orders of magnitude, and we have a net gain that's 4. And recently we've reached here even close to 5 orders of magnitude enhancement there. So that's the whole benefit, that's the whole point here in moving to an integrated optical configuration to detect things that are happening on that interface. All right, I mentioned to you there are several modes on you can get several modes on your waveguide there, but not all the modes are born equal. you, for instance, if you calculated that sensitivity factor there, and this is what we call the V number there, probably many of you may be familiar with that, essentially is the thickness normalized by the wavelength you are using there. And as you increase, for instance, the thickness there, you start to see showing up more and more modes. But you see that as, for instance, this sensitivity factor is very high when as soon as it appears, it goes very high. And then as you increase the thickness, that sensitivity starts to go down. And here you have the solvent dashed line. Those are the two polarizations you have in your system. And as you increase the thickness, that fundamental mode is losing sensitivity. And then you have the appearance of another mode, for instance, the mode, the next one is going to give a higher sensitivity, but it's not going to reach that high peak that you have there. So this tells us that if you want to work, if you want to maximize the response here, we want to work in a single mode configuration. And there is another reason also work for single mode. If you have a structure that has multiple modes there, you're gonna come put light into several modes. You're gonna measure something here, and then you don't know how much power you put in each mode there, and then the information you got here is not going to be able to tell much about what is going on with that interface there. Interrupt me anytime that you want.
Все окей? Промовите. Окей.
So that's the whole idea there. So we're going to be working with single mode geometries that are in the order of 200 nanometers, and we want to detect that a lot of the applications that we envision here that we are using this is for proteins that are typical numbers of the order of a few nanometers, and they're going to propagate several centimeters there. But a lot of things that I've been talking about, you know quite well. And a lot of things, this are integrated out, has been developed for the telecommunication window, 1.5 micron, 1.3. And but there are not many biological material with transition bands on those regions. That's why the telecom window works nicely at 1.5, because many proteins are transparent to that. So in our case, this is playing against us. We need to develop technologies here that go and reach the transition band of our proteins. So we need to develop technology here that works fine for the visible and lower on the short range of the visible there. So here is an illustration of several of the biological material of interest there. Several proteins are represented here: elastin, flavins, collagen, and a lot of things is happening, as I told you, on the blue-violet region and towards the UV. So that this technology is easy to demonstrate in the infrared, in the long visible there, but it's not that trivial, and we've been working on this and pushing this technology to a broad spectral range, including good part of the ultraviolet. That's where, for instance, if you're taking a protein, most of the proteins there, the aromatic groups that are very universal to the polypeptide chain of the proteins, those polypeptides, they are aromatic groups, they have transition bands that are on the UV there, and that's where we make the technology universal. If we can reach that level, then we're going to be able to detect many, almost any type of protein there. So a good chunk of our work is how to move this technology towards the UV there. So this has been a project that we worked for a few years, funded by the National Institute of Health in the United States, and how to take that technology that works in the infrared towards the UV. And we know there are two challenges there. The first one is how to get a low loss optical waveguide that can reach that level. So the choices here are not too many. I mean, in terms of getting transparent waveguiding materials there, the choices are, silica, maybe silicon oxynitride, a few fluorides, and currently a few fluoropolymers start to show up. But on those options, this is not a very robust waveguide in our opinion. Fluorides are very hygroscopic and can be problematic in changing their optical properties. And second, they're extremely expensive. And the problem we work with silicon dioxide is that you still need a substrate that has lower refractive index. So if we choose like silica, we would have to use like a magnesium fluoride as a substrate. That would make things extremely costly. And I would burn all the money that I had for my research grant just buying substrate for implementing this project. So we knew kind of from the beginning that we had to use like film materials like aluminum oxide there. And we focused on that, and having understand what the material should be, we did attempt several fabrication processes to deliver good quality waveguides in that range. So here in black is a list of our failures. We tried several technologies, E-beam, RF magnetron, ion beam sputtering, Sergio, and the propagation loss was huge. And keep in mind that we are interested in moving to characterize waveguides that work, for instance, at 400 nanometers. So that, although, for instance, you can certainly have a very low loss when you go to 1 micron and above, when you start going towards like 400 nanometers and even below, that's a tremendous problem. We saw tremendous loss using those technologies. So the only reason I'm talking about to you today about this is because we were rescued by this technique here that's called atomic layer deposition, that we are able to successfully reach good quality waveguide based on aluminum film. For those who are not familiar with atomic layer deposition, it's a type of chemical vapor deposition. It's 2 steps. CVD, you have a surface that you want to coat, you bring the 2 precursors to the surface, they react, and you keep growing your film. Atomic layer deposition is a 2-step. In a way, you take your surface there, your OH groups on their surface, and you introduce your precursor. In the case of alumina, what is the precursor? The first precursor is 3-ethyl aluminum material there. And this you're going to form covalent bonds there, and you're going to keep getting covalent bonds of that precursor to the surface until you completely fill all that interface there. And this is a monolayer process. It stops. It's self-limiting. It doesn't keep growing. All you get is a monolayer on that interface. So it's a conformal coating. It doesn't matter what shape you have. It's just going to form a monolayer of that material on that OH surface there. And once you reach this full monolayer of that material on that interface, what you do, you close your chamber there. And what you do now, you purge. You completely remove that head space there, and then you introduce, after you finish that purging there, you introduce your second precursor. In this case is water, and this water is going to react with that interface there, and this is going to happen the same way. You're going to form a monolayer there. In this case, you're going to have your oxygen attaching at the end of this process there. You're going to have this OH group completely grown on this interface there, and this is again self-limiting, and you're gonna, at this point, you're gonna stop again, purge your headspace, and start all over. So you can grow layer by layer there, and you're doing this covalent process there. You make a very robust film, and you get something that provides good quality of waveguide. The results that you get out of that is something that is shown here. On the left corner there what you see, this is just the refractive index against wavelength. This is just showing the dispersion of material. This is giving us that we do have a high index material that we can work with, but this is not a really big deal. I mean, this is just a characterization. The important feature for us is here, is the loss per centimeter that we get, and we see that over a broad spectral range there, we are getting attenuations that are very low, and here is a demonstration. This is a picture from, you have a grating coupler here, you have a grating coupler there. We're shooting a 325 laser beam on that edge there. The beam is propagating all the way. This is about 3.4 centimeter in coupling there. What you see on a piece of paper is the end line that the light 325 has propagated all the way in its coupling there. So any more details can be found in this paper here that we published a few years ago, and we have all the details on this fabrication process. So this is a result that enabled us to go to a spectral region that was very attractive for our detection.
Коллеги, хотелось бы подчеркнуть, что люди работают не там, где удобно, в телекоме, где все хорошо светится, а там, где надо, там, где хотят биологи, и приходится поэтому преодолевать массу трудностей, но это получается. Используя кучу материалов, кучу методов, в итоге приходит к тому, что это можно использовать вот в таких сложных задачах. Спасибо.
So this is the first hurdle is to get something that can guide light from point A to point B. The next step we had is we want to do spectroscopy. A lot of applications in integrated optics is based on a single wavelength. You want to couple a laser beam at one particular frequency and deal with that. As you saw here, we want to do spectroscopy over a broad spectral range. So we want to couple several colors at the same time to do spectroscopy. So we work on our way to find a way to couple that broad spectral width. And this has been a problem that people in the early 90s has been work with, in particular, people looking on using integrated optics for optical data storage or readouts in CDs. And what you're trying to do, you need to want to couple broad spectral range. So in the literature, this is known as the achromatic coupler problem there, how you have dispersion on couplers, both prism coupler and grating coupler. So people has been having predispersive components there in order to compensate for the dispersion or the mismatch on the effective index in your coupler, and several techniques has been proposed in the literature there. The bandwidth is rather small, and there is a huge problem getting those alignments properly set there. So this is something I've worked, and I have several approaches published in the literature there. I'm not going to discuss all the generations of approach that we've done along the years. I'm going to just mention to you the one that currently you find in my labs there that work nicely and so good. It is friendly enough that we can create an instrument based on that. We all know that if you have a grating there and you want to couple a broad spectral width, you know that each color is going to require one particular angle there. So if you have a certain pitch that is known by this number there, an effective index, you know the central, this is the grating coupler equation there. If you have the central wavelength is based on the pitch and the effective index, and the spectral width is going to depend on two terms there. One is the periodicity of your grating, and the other is the numerical aperture that you have on the beam. The broader the angular width, the broader the numerical aperture, the broader the spectral content that you can get. So learning that we borrow one particular solution. People in microscopy know this very well. If you want to resolve better, I mean, if you want to go to a smaller diffraction limit there, you want to go to smaller spot size, you want to increase your numerical aperture. So what they use, well, in many cases, you use index matching, and one possible solution, you use a solid immersion lens there. So this is a solution that we borrow from microscopy there, that what we want to do is you want to use a solid lens here attached to the substrate, and this, as you increase the refractive index here, you increase the numerical aperture. So that's the approach we've taken there. The approach actually has been published on this a couple of years ago, and it involves several tricks there, a lot of things that needs to be paid attention, and this is the part I mentioned to you. We have this grating there, but you know that you're going to minimize optical aberration in your beam. You want to make a beam here that on this plane here makes a point. You want to minimize all this blur that you have on this interface, and out of the board and into the board, you want to make a line there. So you want to have a line, so you need a highly anamorphic beam, and that is diffraction limit there. So the solution we use involves using some astigmatic solutions of, and there are not many cylindrical lenses commercially available in order to play those tricks. So that involves several tricks in order to minimize that blur there, so you don't lose too much of energy there. So, but this is something you can find more details on the literature there that we're able to successfully implement. So you get this very, very nice astigmatic beam that is focused down on this point, and then what you have this line beam propagating out, and then you have another grate on the other side that's going to shoot the beam out, and you couple that to your spectrum. So that's the configuration that we use. This is how this critical element here is the fabrication of this diffraction grating there. This is done, I'll just say a few words. I know there are people here that has been involved in the lithography of things that involve some of this fabrication. What we do in terms of writing that periodic modulation, we use something that's called Lloyd's mirror configuration. Essentially, this is you have your substrate, we coat with a photoresist, and we come with a beam, a helium cadmium beam with a flat wavefront, either 42 or 325, and part of the beam goes straight to the photoresist, part of the beam reflects there, and you have this two beam interference, and it creates a periodic modulation there. Then we put this on a developer tank, and the critical part there is when do you stop this development process there. And we use a Hemi beam that doesn't create any artifact on the photoresist, and as you develop, we monitor the diffraction efficiency there, and we monitor and we know where to stop that. If you're monitoring this at the literal configuration that you have the force reflected order going back on itself, you want to stop this when it transmit this first diffraction order in transmission hits its maximum, and you get your photo pattern. The idea is to make a photo pattern that's 50% open, 50% covered. And you can learn more details with Sergio that's sitting back there. He spent some time in my labs doing that. So you have an in-house expert. Okay, so at the end of this process, we got this photo pattern, and then we got to transfer. We want to transfer those patterns that we have in photoresist to the glass, and one technique that we use, we're using ion mating. We put this sample in vacuum there, and we bombard with argon ions there. At the end of the day, we have this trapezoid structure here. This is a piece of glass that we have written this periodic modulation there. And this bar here is 200 nanometers. So we have features there that are very regular and very nice for our coupler there.
200 nanometers periodic structure.
This one here. Okay. So this is something that we develop in our labs for some times, and we use quite routinely. So when we put all those pieces together, we have, this is the real representation there. This is a cross-section of what you see here. If you take a cross-section, this light comes, for instance, if you're having broadband light coming from a fiber, this, you have the divergence, you collimate, and here's a place we put polarizer that I'll go in a little moment. And this is a cylindrical lens, one, cylindrical lens, two, and then we have a piece of glass here, and on top of that, we have another piece of glass with the gradients, the waveguide, and the molecules we want to probe. So what you see on the white here, this whole thing is fixed. This is the part you're seeing from this top view here. You are seeing all the whitish part there. So this whole thing there stays there all the time. So we fabricate the part that you see here in gray and yellow, and we just drop that piece into this square here, push to a corner, and we're good to go. We can close our chamber there, and that's where we start to bring our proteins of interest, our biomolecule, and do the studies we want there on that interface there. So that's a very practical, and we want to build an instrument that can routinely change the sample out of this chamber. Okay, so let me show you a couple of applications that we implement this technology. Here's a case that we inject cytochrome C to that chamber there. We let it incubate and form a monolayer, and actually the fraction of a monolayer that we got here for us. When I say a full monolayer, this is considered you take a protein and you have it stamped one protein after another that you completely cover the surface. So we are dealing with concentrations here. That's only about 2% of that full coverage there. And when you have concentrations on this order there of, let's say, about 5 nanograms per centimeter squared, we are getting absorbance here of the order of almost 1.5 and above. If you try to do this in your regular spectrophotometer, there you get nothing. The whole signal is negligible there, is on the noise level, and here we can reach a very strong signal. Anyone here is familiar with analytical chemistry in this field, you see that this is a very strong signal, very robust, that we can detect. So this is very useful. And looking by what is the minimum absorbance signal, you can detect, you can retrieve things that are in the order of a picogram per centimeter squared. So this is around about 100 times better than what I was mentioned to you as the gold standard. So this is a very important figure of merit from what we detect. But I believe the most important feature is not on this number here, but on the fact that now you're seeing this over a broad spectral range. We are getting signal here that are over the full spectrum there. If you remember the surface plasma resonance that I was mentioning to you at the beginning, the only thing you can detect is how much is going to that surface. You can get a number, what is the mass. But for instance, if you have interference, you have several molecules that are competing for that spot on the surface, you cannot tell anything. When you know the spectrum, you know you can have a discrimination of what is going on this interface, who is going to this interface there. But more important, as important as that, is that even, for instance, you can understand what is happening with those molecules as they absorb them. Many times, when I mentioned to you, when the molecule goes to the surface, it changes conformation. As it changes conformation, we will change its spectrum absorption band. So this is something that we shown it here. This is a work from a few students in my group. That this is let's focus on this plot here. This is the molar absorptivity This is the fingerprint of your molecule. This is how much light you absorb per mole of the molecule there. So this is independent of the amount. And as you see here, this is an experiment that we start to change the concentration, making the density of molecules on the surface smaller and smaller and smaller, and we start to see a change on the molar absorptivity of your molecule there. So this is what is happening there. The molecule, as it has more space to evolve on the surface, it starts to change its conformation and it changes transition there. What's happening here is the molecule, as it is unfolding, it has solvation of some hydrophobic groups that are potentially hidden when it's totally surrounded by water, and it goes to the interface. You start to see those transition changes there, and you see a spectrum. So we can capture here conformational change of molecules as they go to the surface. And this is a big deal for people that are involved in understanding process. For instance, when you mobilize an enzyme on a surface, many times it loses its activity there. So many people have cartoons and say, hypothesizing that the molecule has changed its conformation. Here's something that allows us to go and probe if this is really happening. So we can start looking at this interface spectroscopically. This is something that is not possible to do with SPR.
Еще пару слов. То есть вот по двум последним слайдам. Первое — громадное увеличение, в 100 раз больше чувствительность, а второе — просто превосходно то, что мы работаем с широким спектром, и мы получаем на порядок больше данных по сравнению с плазмонным резонансом. Мы можем к каждой длине волны сопоставить молекулу в каком-то состоянии, не молекулу, а частичку, лежащую на поверхности. И если что-то меняется в спектре, где-то в одной длине волны, то это можно интерпретировать. И этот процесс можно еще и разложить по временным параметрам, рассмотреть временную эволюцию. То есть биологи получают инструмент, который на 2-3 порядка мощнее по сравнению с тем эталоном, который используется сейчас. Это, конечно, очень круто.
Это за счет светофильтров и там просто спектр выходной.
Там широкий спектр.
Нет, я понимаю, что там галогенка, но я призму имею в виду, которая в спектр раскладывает.
То есть там на выходе что, спектрометр?
How do you measure a spectra?
How do I measure the spectra using the waveguide? We're using the here. So we have a broad spectrum coming in, this propagates, and this broad spectrum come out, and we set this to a CCD that we have each column there arranged to a wavelength.
With what resolution of your camera?
Of the CCD camera, 1-2 nanometers.
Сколько элементов достаточно? 512 024. Это ПЗ смотрится.
How much
Это
elements?
ПЗС плюс.
Как на спектр чувствует?
Это спектрометр, вот то, что...
Спектрометр.
Да, не
Там
просто
должна быть-
ПЗС.
Там должна быть и призма какая-нибудь или что?
Ну, они говорят, что там решетки стоят.
How many elements is
А, ну,
А,
просто
просто
такая
спектр
Они складывают.
Everything is clear.
Чернова.
So we have a visitor there that can clarify. So let's see if we agree here. We do have a spectrograph. I don't think I have a picture here. This light couples to a fiber. This fiber delivers the light to a spectrograph dispersed, and we have a linear array with 1024 columns there, and we have we take pictures and we can collect this back.
Okay, let's move on.
We're good?
Рома, по следующему слайду вопрос. Ну, следующий.
Next.
Next.
Next slide, please.
Next. Ага. Вот разным веществам соответствуют разные пики. Вот тут вот
Разные картинки даже.
разные картинки.
А,
Или, то есть, если скажем, это для одного из типов веществ, да, измерение сделано?
По-моему, да. you have
Это
this graph
один
for only
протеин,
one
разные
subject?
концентрации.
Да. А если там два протеина?
If you will
Два
have
раза.
two different proteins,
So that's a
Как будет выглядеть картинка?
will you have any different hour peaks?
certain. Once you have, for instance, this is was done with a single kind of protein, and we're looking how they change if they change their spec. But if you're having a solution two proteins and you want to know which one, I mean, you have competing there, the spectra you're going to get depends on the fraction of how much of each type of protein goes to the surface. So this is the same issue that you have in solution. When you have two proteins in solution, the spectra you get depends on the concentration of each of them.
Расскажи.
Получается, что спектр будет зависеть от содержания, от соотношения протеинов.
Ну и в разных местах будут пики для разных протеинов.
Видимо, да.
Интерференции между ними будут?
Нет,
Между отраженными волнами от разных протеинов.
All right. Here's another example that we're taking like a chlorophyll A, that it's an important organic molecule that shows up in many configurations, and we, in particular, they are present in our phytoplankton cells involved on many steps on the solar carbon fixation that we have from solar light. And this shows up, I mean, in several different environments. So we look at how this protein, I mean, would behave on different interfaces. So we took our waveguide there and we functionalized in two different ways, using, for instance, a hydrophilic and a hydrophobic chemical groups to this interface there. And we look, for instance, how those interfaces there, if they would by any chance change the behavior of that chlorophyll A. And we also we want to understand how the ionic strength, the amount of salt in solutions, for instance, would affect the immobilization of this particular molecule on the surface. So, for instance, this is a chlorophyll A, particular in neutral pH, and we have different salt concentrations. And this is the solution spectrum there. We don't see any change. I mean, it's roughly the same spectrum that you get in solution, and those molecules is in solution is about the same. But when you look at what is the spectra that you get when they go to the surface, for instance, if you look at the ones that are going to the hydrophilic surface there, you have a substantial change, a spectral shift there. And if you look at what is the different salt concentration, there is a substantial difference as you go, for instance, from what we call, this is how the concentration on the surface is growing as for different ionic strength, and you see a substantial difference from one behavior, from one ionic strength to another. So those are kind of studies we can start looking at, and it's important for several people in surface chemistry to start to understand what happens at the monolayer level that is happening on the interface there. So this is another illustration how things work at that level, that we can start doing a lot of analytical studies that was not possible to do when you just have a tool that just measures the mass there. Well, looking at the spectra there, you can learn a lot of new things. In addition, we are reaching limits of detection that's already more than 100,000 times better. And this is being done by graduate students. So this is, we are not certainly making this as $400,000 per tool. This is a mass produced, as I mentioned to you, and once we have this white part there set up, all we are fabricating is this top slide there, and we drop in that interface, and we can do a lot of research on those interfaces. Well, But the potential doesn't stop there. I mentioned to you that we do have a place to put a polarizer on the optical path. And for instance, we can bring light with two orthogonal or with different polarization on that interface there. And for instance, if you have a molecule where the transition dipole, for instance, is at a certain angle on that interface, we can start capturing that orientation there. If you measure the polarization in each, you measure the absorption in each polarization there, and then you know the properties here of this film, essentially you know the refractive index profile, you know the refractive index of water, the refractive index of your waveguide or your substrate. We can calculate what is the electromagnetic field, and we can calculate, essentially this is the path length for measuring absorbance at the polarization, at T polarization. This is for the TM polarization, and we can look at those quantities there. We can retrieve essentially what is the average orientation of this molecule on that interface. And many people that are in chemistry, and you want to understand if there is order, if you have grown a monolayer there that is highly oriented there, or if it's randomly oriented, this is a tool that allows you to capture that information. So we can certainly get that information by just look at a simple experiment instead of measuring one polarization, measuring both polarizations.
Понятно, да, идея, что еще можно подключить в качестве носителя информации поляризацию, и тогда разная поляризация будет поглощаться или взаимодействовать с этими частичками на поверхности по-разному, и мы сможем определить и средний угол, и если существует порядок, то найти этот порядок или сказать, что там беспорядок. То есть получить еще больше информации о том, что происходит на поверхности.
But I think the result that I'm showing here, the method that is present here, is based on one strong assumption, that you know what is the refractive index of this film here. And you make waveguides in lithium niobate, you know that this is a tough problem to know this index profile there. And if you have something like it's a graded refractive index, all the theory is garbage. So we need to find a way to overcome that. So this is something that we found a way to go around. Is instead of doing one experiment, one measurement, we do two measurements. Let's say you have a graded index waveguide there, and first experiment that you do, you put something here on this interface. You're going to measure the absorbance again with the two polarization. But you put first something here that's totally random. Either you put ink or molecule that has absorption there, but it's totally random when it absorbs to that surface there. And you measure what we call the dichroic ratio, that is the ratio of the absorbance, like in TE over the absorbance of TE over TM of what we call the isotropic molecule there. Okay, you measure that ratio, and then you clean that, and you add. Then you start doing the experiment that you are interested in find out if, for instance, your molecular layer that of your particular protein, if it has order there or not. And then you do the same thing. You measure the dichroic ratio of your sample there, and you ratio this term over of your sample over the top part, the bottom part there, and from that, then you can retrieve what we call the average of that orientation of your molecule to that surface. This cosine, the average of that cosine there. So this is the, let me see if I'm citing, this shows up in this paper here that we demonstrate all the math and how to get to this result there, and how you can treat here graded index waveguide, or many times, for instance, we have multi-layer waveguides. I've shown you here the very simple one that has just one layer, but many times you want to have 1, 2, 3 layers there, and many times it's difficult to characterize precisely what is the refractive index and thickness of each layer, so that initial theory that I mentioned to you When you have multi-layer, it's not going to work. So, but if you do these two experiments instead of one, the bottom part here when you're doing the isotope is essentially calibrating the dichromate ratio of your system, and the top one is for measuring what you are interested in. And having this number there, you can plug in here and find out what is the average orientation there. For people developing materials on the surface, this is a crucial number there. Find out if you have order on the molecular film at the monolayer level that you do. This is an illustration that we demonstrate there. We took a particular waveguide and we likely use this rhodamine D dextran there. This has several high coordination there, so you have several absorbers per molecule. There's highly random on the surface. We measure the dichromate ratio. This is the absorbance in the two orthogonal polarization that I mentioned to you. So this is our calibration. And then we put a sample there that is, we knew for sure that this particular, with this alkyl chain there and has a transition band that is right on that interface there. We knew that it was highly organized when it goes to the surface. And we measure this dichromate ratio here. You see this is totally different than that one that is isotropic. And by ratio, the dichromate ratio of this sample to that one, we can retrieve what is. This is for people that work in surface chemistry. This is a second order Legendre term that defines the order of the material. If you have this number equals to 0, means that's totally random. This number away from 0 shows order there. So this is a crucial part that you can demonstrate that with this two set. Want to go over that? Should I go?
Yep.
How are you doing on time, please?
Силы есть. Еще в одном проекте послушаем. Yes? Okay.
Okay. So I'm not going to abuse of your patience here, so let me go a little briefer on the second topic here. So one of the things that I show you was based on absorption, transition bands, and molecules on that interface absorbing light. A particular problem that we are interested to use this integrated optical device is based on something that I initially worked with my collaborators at the Los Alamos National Lab in the United States, that we are trying to develop a cholera toxin sensor there. And my colleagues, they found a way that, a very ingenious way that, for instance, you take a solid interface, you have what is known as a lipid bilayer. And this is this lipid bilayer is unique in the sense that on the bottom part here, you make covalent bonds, and that is anchored, it's fixed on that interface there. But at the top part there, it's kind of a fluid. This is a two-dimensional fluid what you have. So what you do, you disperse on this top layer there two kinds of fluorophores there, and those are markers, and they are, when they are close to each other, if you excite one, it transfers the energy to the other one there. But in principle, this is randomly distributed on the surface there, and if you come with light here, let's say blue light, to excite that fellow, and they are not talking to each other, those two fluorophores are far from each other, so they just, this blue one just gonna emit light, and you got some particular signal out of that blue light, of this blue excited, in this case it's the diamond there. So the sensor works when you bring like this cholera toxin. This is a multivalent, in a way, it's gonna attract several of those, this is optically tagged in order to attract several of those fluorophores close to this protein there. So as this protein goes to the surface, it's gonna bring many of those fluorophores close to each other. And if you're keeping exciting this, and you have those like these blue and red fluorophores close to each other, you have a process that is known as energy transfer. So you excite this one, and this one is going to excite that one, and you're going to have a stronger emission now. You're going to start seeing a depletion of the emission of this one, and an increase on emission on that one there. So this is what you observe as you absorb like the color toxin to this interface. This is one is going down, and the other one is going up, and you measure this contrast. You can detect this presence of this particular toxin to the surface. So this is something that we apply for a patent. It works fine, but we're looking for something to go beyond that and make things that this is started to be mass produced for third world countries that can buy this inexpensively, making disposable device. What we look for, I mean, we here, if we're gonna do this, we're doing this by taking a lining lens to image something that is happening on a few nanometers of a layer there. That's certainly something we want to avoid. I mean, if you want to make something disposable there, we certainly don't want to have this critical alignment there. So we want to avoid doing that. We want to look for something that is easier to implement and can be mass produced. So here's another. I think I can, for sake of time, I can skip this one. What I was going to, this is just another way to motivate you for what we're looking for. What we try to do is, the question we ask ourselves, can we find a way that when this light emits, instead of, can I find ways to take that light and put back into the waveguide? I have something that is emitting light the outside, can I find a way to put this back? Let's say I come with this blue light to excite that one, that emits red light, can I find a way to put it back there? If I can put it back, then I can, at the proper place, I can outcouple that light and transfer to my detector there. And if I can make this inexpensive, I can replicate, that's something that we avoid those troubles that I was mentioning. Looks like, I mean, if you look back, I mean, what we know from elementary optics there, this is a low refractive index, this is a high refractive index, and the light is guided there. When I have light propagate inside of this high refractive index beyond total internal reflection angle. And that's the only way you get it bounces back and forth at total internal reflection there, to get this guided mode there. So if I go back to our basic optics there, we know that any light that comes from a low refractive index and goes to a high refractive index, any angle here is going to be limited by the critical angle. You're not going to get any light here, no matter what angle you have, that's going to go beyond the critical angle. So it looks like we're looking for something here that's impossible to do, but not so fast. Okay, this part of what we learn in elementary optics actually is based on the fact that we are doing plane wave decomposition. We are considering light wave sources that are far away and decompose that into plane waves. Well, this problem is not, this approximation of plane waves is not the best one. Certainly, this one here may have evanescent fields there that will overlap with the evanescent fields of my waveguide there, and this overlap can transfer energy from one process to another. This is the representation of the possibilities there, that you have this overlap that can affect that coupling of light from this emitter to that guided wave there. So this is a question that we ask ourselves, how to make this process more efficient, coupling light from this emitter to that guide.
Пара слов. Понятно, да, что придуман датчик холерного токсина. Как опять же говорят биологи, штука очень важная и применимая, например, для тестирования продуктов питания. Есть там холера или нет. Как это работает? Холера, садясь на поверхность, облегчает трансфер энергии между донором и акцептором, и мы получаем свечение на другой длине волны. То есть как только она там появилась, сразу у нас в спектре появляется резкое изменение. Но простая и, казалось бы, невозможная с точки зрения обычной оптики проблема. Вот этот свет, который над волноводом, завести в волновод показатель преломления, который значительно выше.
So that's the physical problem we try to solve here, how to make this process more efficient. And the motivation again is commercial. You certainly know about this. If you go to Thorlab's catalog and you look for what is the price of a fiber that we have 2 FC connectors there. This is a fairly old slide, so don't take this price and this is the United States price, but it's roughly this number there. And then if you take a diode laser there, and this is about $60 there. So these separate components, this is something that is very reasonable. But when you ask them, when you're gonna buy the product that is this one combined with half of that fiber, when you cleave that fiber there, just take half of that piece, you're paying this price there. You guys know this very well. This is in production of the integrated optic components, a big thing. Alignment and maintaining that alignment for the life of the product is extremely challenging there. So there is a lot of cost on this. So if you can,
We will take much cheaper.
I'm sorry?
We will take much cheaper.
Great. But if you can make things that are fully integrated, you can develop the mass fabrication of the device, you avoid those kind of things. So that's something that we're trying to do. So as a physicist, what we're trying to ask here, okay, let's say the emission of this dipole here into that waveguide here. Well, here we're going to do a decomposition that's not plain wave. We know that there are many ways you can take the electromagnetic field and decompose on a complete base. Here what we're going to do, we're going to take the bound modes. You may have a few modes there or a discrete number of modes, and this is one set of this expansion there. But you have another set, a huge number of other modes. For instance, you have the substrate modes, light, for instance, that would represent by ray that are coming here, and like having total internal reflection coming back here. So this is a continuous number of rays that can have that kind of profile there. And we call that substrate mode. And you have another set here that we call the cover substrate radiation mode. That it comes here, and part we're gonna transmit over the cover and transmit over the substrate there. So we have on this green and blue here a continuous, an infinite number of modes there, and we have some discrete modes. But when you combine all that, this will we create a complete base that we're gonna decompose what is the emission of this, and we're gonna project how much of this is going to go into that, or into that, or into that. Essentially, we're looking for that coupling of the transition dipole into particular electric fields, and we're going to describe all those fields there. And this is something that my students work hard to get it done, and I'm not press you on all the details here, but you have a discrete number of bound modes. And this is done by like the T modes. We have a continuous number of modes for the substrate and for the cover substrate. Essentially, here you just have the EY polarization as you just have the T modes, and you're going to normalize each of those modes there. And then you have for TM, you have two electric fields that what those two columns represent. So now let's go to the applications. Essentially, this first cartoon here, it tells us as I vary this position of this dipole, of this emitter, as a function of the height here, how much of that light will couple in each of those types of mode. And here we're gonna sum all the light that goes to bound modes, all the light that goes to substrate mode, and all the lights that go to cover substrate mode. That's what those cover represents here. Red is bound, green is substrate, and blue is cover substrate, and black is when we add all of them. We are moving this dipole in different heights there, and we calculate that coupling for different polarization there. Obviously, when you get the dipole, this is where we're doing this calculation for a particular wavelength, we take a wavelength that is 1 unit of that height there, and we essentially scan this molecule in different positions, and we find how much it goes to different types of mold. And you can see that it does get stronger when you get to the substrate mold there. And we want to find out, and this we add both of them, we want to find out what are the favorite conditions to increase. What we want the most is put the light into the red stuff. That's what we want the bound modes to be enhanced. So let's see what favors that process. So the first thing that we did, we compared. We took two kinds of structure. One was a single mold that we have the height equals the wavelength, and then we took one that the height was about 3.6 of the wavelength. This one has 4 molds, this one has 1 mold. We took one refractive index 156, and we put in cover and substrate refractive index 151 and 133, modeling usual conditions that we have. And the reason we ask yourself, can we get more light if we make it thicker? That's what we're trying to answer with this model. And we see that the answer is no. We see that, for instance, the bound modes here of the solid line that's single mold and the feeder line that is multiple mold, it gets about the same amount of light. The bottom line is that making the waveguide thicker, what you get, you get 2 molds, but the interaction becomes weaker, so you don't get more light. So the answer to this question is no. But if you go on the other case, in this case we're going to get single mold and multi-mold, 4 molds again, but instead of changing the thickness, we're going to make the waveguide with a higher refractive index. We're going to keep the same ratio of height of the thickness over the wavelength 1, but we make the refractive index higher, I get way more molds, and you see a substantial difference on that process there. So you get way more light coupled to that structure using a higher refractive index. And then we ask ourselves, obviously this was calculations done for all sorts of heights, all positions of this molecule, different disease there. Then we ask ourselves, okay, we want to make the Z equals to 0 because the relevant problem here, for instance, if you're developing a fluorescent sensor, is that when that molecule is immobilized on the surface there. So we ask you, when you put that Z equals 0, and we calculate as we change. Again, we're looking how as we change this V number, again, this is changing, for instance, the thickness there. And you see that where is this sweet spot, where we might maximize this process. And we see that it's maximized right after you have the appearance of the first fundamental mode, and this process doesn't improve. You can keep increasing the thickness there, and you're not going to get more light. Actually, it is going to bounce back and forth around the midpoint there, and it's not going to get as high as you would have at that point. So this tells us that the sweet spot is on that range. Single mode is perfectly fine, and actually it's going to be the best in order to collect the light that is produced. And this is how that the power is distributed among several modes. For instance, it is this curve here represent for how much each mode is collecting from that system there. But when you add all those contributions, you add all this amount, you're getting the trace that's on the top of that. And as we change the refractive index, as we go, for instance, from 150 all the way to, let's say, 2.3, things that are possible there, make waveguides with higher refractive index for this kind of application, you can substantially enhance the amount, the power that you can collect through your guide. So this is extremely useful measurement that you can be very important practically, that it can help you in terms of improving the efficiency of your device. We also took this a little further. We can also look, is there a particular orientation of molecules? If you can to have control on the orientation of the molecule, and you find ways that if you want to favor a particular orientation there, is this gonna, can you gain anything of that? And we found that yes, depends on the orientation that you get on that molecule, you may be able to enhance how much you get for each type of mode. So I think I already spent a good chunk of your time here, and I will be glad to take any questions.
Вопросы? No question?
I have a question. Regarding your, could you show me the previous slide with the dependence of, yeah, exactly maybe this one. Well, no, the previous, about modes, yeah. So, this slide means that, for example, the second, if you will use two mode waveguides, the difference in how to say, emission efficiency of the device will be about 2 times concerning to single
You're
mode.
talking about this plot
Yeah.
or this plot?
Yeah, about the left.
That one. So this is, again, this configuration, this trace here is all the added power that is guided. So you say that here there is no mode,
Yeah.
cannot guide. And as you increase the thickness, as you go a little bit beyond the cutoff, then you get to the what we call the sweet spot. That's when you get most of the light. If you keep increasing, the amount of power that you're going to guide is less. And then comes another mode. And that second mode is going to help. And that second mode is going to help, but it's not going to help as much as you could get there.
Yes, but my question is actually about the cost efficiency maybe, because if we will, you said that in order to produce high quality waveguide, single mode waveguide, we need to use atomic layer deposition. I guess this is also applicable for this situation. Yes?
It can be used certainly.
And a rest pattern or something like that, it will not work for this single mode waveguides. Am I right?
Well, this is you trying to maximize how much light we're going to get into the. So that one reason there is no point in making a thicker waveguide, spend more time on the fabrication, where you're not going to get any gain on the enhancement of light that you're going to collect.
Okay. Right. Thank you.
The naive expectation would be, I make it thicker, I support more modes, and I get more light. But these calculations tell us no.
Thank you, Professor.
Sure.